Alrighty. Um, I'm gonna need somebody to tell me what our one goal and our one mission is. Axel.
To glorify God
And?
through excellence and obedience.
Okay. I don't think everybody heard you say it, so I'm gonna need you to project.
So the goal for this class is to glorify God through excellence and obedience.
Very good. Everybody hear that?
Yep.
Okay. In light of the revival services going on, I know a lot of you are probably very opinionated about what's been happening, and trust me, as a theology major, I can relate with you. That being said, I would very much caution against judging, because to the measure that you choose to judge other people, so your Heavenly Father will judge you. Does that make sense?
Yeah.
In this class, we are going to be doing mathematics, and funny story, mathematics was made by the God that we were just kind of worshiping in chapel. And so it is my expectation for this semester that this classroom becomes in itself a sanctuary and a chapel in itself. We do chapel in here. We don't necessarily sing, and we don't necessarily listen to a sermon, but we're going to be studying His creation, and we're doing so with purpose. We're doing so with intent. We're going to do so to glorify Him. There really is no good external reason to do anything difficult, except for doing it for your God. So if you believe that He is your God, and if you believe that He is your Lord, I simply ask that you treat Him as such in this classroom, and you honor Him with what you do in your work, in your studies, in your discipline, and keeping up with the coursework. I understand that it's a lot to ask of students who are busy in college. That being said, I can also understand and relate with you on that front, okay? But don't let that busyness become an excuse to offer up to God a lesser sacrifice because you simply don't want to. Does that make sense? Okay. I am making the assumption that you know everything that was in lecture 1.4 because now there was a news item and it was uploaded a few days ago. So I'm now proceeding into 1.5, which is going to really kind of frame some of the discussion and the intuition that we've been building up to. So it's a shorter section. Hopefully it's more straightforward section and more practical in the sense that, yes, there's some theory, but we'll do mostly examples as the lecture content. Make sense? So we'll talk about, we've talked a lot about setting up the ways we could represent the problem, but we really haven't talked about just simply solving the problems, which might become a really helpful thing as we move forward. So we're going to talk about this. There's really two kind of families that we're going to think of, the homogeneous ones and the non-homogeneous. So homogeneous linear systems. And let's define what we mean. A system of linear equations. Linear equations is said to be, and then our term that we're defining that's new is homogeneous. Homogeneous. If it can be written in the form, I can take a matrix A, which is all the coefficients, if I were to write out the system in standard form, some vector x, which is essentially going to represent, in putting in a list all the entries, what those variables are. So if my system had x1 through x4, this vector would have 4 entries, x1 through x4. I want this to equal the 0 vector. So this is what's going to make a system of linear equations homogeneous by being equal to 0. If you took differential equations or are taking differential equations, make that connection. They are somewhat related concepts in the analogous. So the A is an M by N matrix. And our 0 vector here. Notice I'm putting the arrow over it. If the 0 vector appears on an exam and you do not mark it as a 0 vector, I'll assume you just answered the question incorrectly and give it a 0 scalar value, okay? 0 is the 0 vector in Rm. Very, very fast footnote here. Notice that we've typically been saying Rn, so why am I saying M now? Recall that the M is denoting the number of rows. It's rows by columns. And so the reason that's important is because if I have rows by columns, and then the number of entries in my vector is the number of columns, so the n amount, that's why x is in n, and then the output of that product is going to have actually the same number of rows as the original matrix, which is why I can't say n here. I have to say m to specifically mention that the 0 vector needs to have as many row entries as. We'll get more into a computation. That'll make way more sense when we actually do that. And so here's kind of an important note. This is a big thing. So if I take ax is equal to the 0 vector, this always has a solution. Has a solution.
That symbol in front of the AX, is that meant to be another special star? Or
I meant to make that a star, but you are correct in not having any clue what on earth I put on the board.
I was not sure a new symbol, but thank you.
There we go. Okay, so if I take a matrix and I want it, if I want to choose a vector so that that's going to go to 0, there always is going to be a solution. It's not that interesting, but we can technically guarantee that there's always just 0, right? If I multiply something by 0, it'll go to 0. So I can have the solution just be x is 0 itself. And then specifically, I need it to have n entries because, again, x is in Rn. It has the same number of columns as the matrix. And so that's pretty obvious. It's kind of, one might even say, trivial. And so we call this the trivial solution. Every homogeneous system is gonna have a solution by the way that we constructed it. And so the one that's obvious and the one that is just always gonna happen, we just call trivial. It's not interesting, it just comes with it. And so that means, why would we spend an entire section talking about this? Where we're clearly interested not in trivial solutions, but our interest is in non-trivial solutions. Non-trivial. Okay, so a non-trivial solution is basically going to be so long as our vector x solution is not the 0 vector. Does that make sense? Okay. Do we understand what it means for something to be homogeneous, a system to be homogeneous? Thumbs up if that one makes sense. Okay, all that means is I take a linear system, and all of the constants after the equal sign is all just 0. And so it's pretty straightforward. And then we're always going to have a solution, but it's boring. And so we're interested in the ones that are not necessarily just the boring, trivial 0 solution. Okay? Now, let's think back to the very first lecture. There were really only 3 outcomes that you could have with a linear system. You could either have one solution, infinitely many solutions, or no solutions. With a homogeneous, the way that it's constructed, is this a consistent system? I'll reframe the question in vocabulary. If consistent means has at least one solution, then is AX equals 0 consistent? Yes. Because what solution is it always guaranteed to have? 0, right? So every single homogeneous system we're working with is going to be consistent. So whether or not it's consistent isn't our question of study. That's not interesting. We're going to look at the interesting part instead. Is it only the trivial solution? Or will there be some non-trivial solutions, and that's going to imply we're looking for a set of the rest of the infinitely number of solutions. Okay.
One question.
Yes.
So is A supposed to be a constant, or is it all, or is it something else?
Very good question. Let's read the definition. A is a...
Oh yes, right.
No, you're all good. You're all good. I'm teaching you how to read math. It's not easy to do. Okay. Any other questions? Okay. Well, let's do... let's look at one more kind of important thing, and then we'll do an example. The homogeneous equation... The homogeneous ax is equal to, by definition, what should I put here?
0, 0.
Vector, good. Has a non-trivial. What does non-trivial mean in this context? Yeah, it is not the boring old 0. That's going to be true if and only if the equation has at least one free variable. Now, if you need to review your notes on the section where we introduced the difference between the basic variables and the free variables, I would highly recommend doing that. What does it mean to have a free variable? Well, sometimes you can make a system of equations, and say your system of equations has like 3 different variables in it, but then you're only provided with 2 equations. Well, then clearly there's not enough room for everybody, right? Someone's going to get left out. And so the variable that gets left out, we call that free. The other 2 variables will depend on that third one hanging out. And so why does this have any bearing on whether or not we know something has a non-trivial solution? So here's an example, and the example is going to provide a motivation for this. And the way we're going to motivate this is we're going to say, okay, well, suppose that a system doesn't have any free variables. Okay, so we'll take the opposite of this. We need a free variable to have a non-trivial solution. So let's just say, is it possible for us to have no free variables and to end up with a non-trivial solution? So let me take, if I don't want any free variables, I need to make sure that I have the same number of variables as I do equations. So I'm going to have ROO 0S0 0 0 T, and this will be my matrix A. This is not going to have any free variables because we have pivots in every single one of the rows of A. We'll multiply this by our x, and since this is homogeneous, we're going to set this equal to 0. Okay, so I could have also written in the math language, I could have just written out the x and the 0 with its components, so I have R 0 0 0 S 0 0 0 T, and here's a good exercise here. So x has to be, is it in Rm or is it in Rn? N. Okay. So n is that the rows or is that the columns?
Column.
Okay. How many columns are in A?
3.
Okay. So how many components therefore should this have?
3.
Okay. So what should we call this?
X1, X2, X3.
Okay, and then what about the 0 vector? The 0 vector says is in R. Okay, is that the rows or is that the columns? Okay, it happens to be that the rows are 3 as well. So we have, what would this look like? Does that make sense? Construction of both how I know that that is only going to have 3 entries and why that has 3 entries specifically. Okay, if this would have been a 7 by 4 matrix, how many entries would I have put in here?
4.
And then how many here?
7.
If this would have been a 10 by 11, how many here?
11.
How many here?
10.
If this would have been an A by B, how many here?
B.
How many here?
8.
Beautiful. Okay. And so if I multiply this out, I'm going to get R times x1, S times x2, and T times x3. And I know that that's still going to equal what's on the other side, 0, 0, 0. And so the only way for this to actually work here is if, because R, S, and T are constants, then x1, x2, and x3 are forced to be 0. That's kind of a problem, though, if we were looking for something non-trivial. Because if I plug 0, 0, 0 in, what type of vector is that? It's the 0 vector. And the 0 vector is the...
Trivial solution.
Okay, so were we able to get a non-trivial solution by having no free variables? All of these are basic variables. Was that possible? No, it didn't happen. And it's never going to happen. So that's why, if we're going to talk about having these non-trivial interesting solutions, we're going to need more we're going to need more variables, we're going to need more columns per se than we actually have rows. Does that make sense? Okay, so we'll do an example where that is, where we'll actually get to do some of that, right? Example, here's a system of equations. 3x1 plus 5x2 minus 4x3 is equal to 0. Minus 3x1 minus 2x2 plus 4x3 equals 0, because we're doing a homogeneous system. 6x1 plus x2 minus 8x3, shocker, is going to be 0. So if I want to represent this as an augmented matrix to kind of go along the algorithm that we've been doing from the beginning, let's do this as column vectors. What's the first column?
3, negative 3, 6.
Next column.
5, negative 2, 1.
Next column.
Negative 4, 4, negative 8.
And then, since we're doing the augmented matrix, I'll put that down. And then,
0, 0, 0.
yeah, nice and easy. Okay, so the first thing we can do to kind of row reduce is we can take R1 and add it to R2, and then use that to replace R2. I apologize. I did not do a very good job teaching you guys this algorithm on day 1 of class. So I own that as my bad. So I'm gonna work through this one with you again. What I'm going to do is I'm going to start by identifying this is my topmost and leftmost non-zero entry. Okay, so that's the first thing we want to identify. And then I want to clear anything that happens to be underneath that needs to become 0. Okay, and so I can do actually this in one step, so long as I leave R1 unaffected. So I can take 3, and I know that by itself, if I just add those together, I can replace R2. Now, I need to slightly change this number. I need to make it bigger. I need to double it. So I'll double R1. So now, if you imagine doubling 3, that is, okay, so how do I relate 6 to 6? I subtract it. So I subtract away R3 and replace it with R3. So this will make your solving more efficient because you can do multiple steps at one time, so long as you anchor what that first thing is and you're only taking care of the zeros underneath it. If you don't do that, you're going to have arithmetic problems, okay? So if we do that, then I'm going to have the top row is unaffected as 3, 5, minus 4, 0. And then 3 minus 3 is 5 minus 2 is minus 4, minus 4.
0.
No, sorry, I said that wrong. It's minus 4 plus 4, yeah, 0, and then 0. Okay, in the third row here, so I double the top, so 6 minus 6 is
0.
Bazinga, this is what we're looking for. All the zeros under, okay. So what's 2 times 5?
10.
Okay, so subtract away 1 from that.
9.
Double this, negative 8. And then if I subtract negative 8 from itself, then that's actually 0. Okay? And so here, I can scale both of these down to 1. So I'm going to take R2, the second row, and scale it down by 3 and re-replace. And then the third row, what do you think I should scale that down by?
9.
Yeah, just 9. Get it to 1. And then re-replace row 3. And that's going to give me, so I have 3, 5, minus 4, 0, unaffected. And then that's 0, 1, 0, 0, 0, 1, 0, 0. Here's a little trick. Whenever you have 2 of the exact same rows, you know that I could just completely eliminate one of them. One of them is unneeded. One of them is arbitrary. So if we wanted to think of this as a row operation, what's really happening is I'm taking R2 minus R3 and replacing R3. Or you could just think about it as they're the same, one's redundant, so I'll just keep the top one. Always prioritize the top one. So we'll have 3, 5, minus 4, 0, 0, 1, 0, 0, and then now we've cleared out a whole bottom row. Okay, so by this point, we haven't even finished completely reducing this, but we know there's going to be a free variable because one of them got blanked out, and there's 3 variables, but only 2 of them seem to be at play here, okay? Oh, I need to erase this. Just so that I know you're on the same page. Does it make sense when you're allowed to do multiple steps to save time underneath it? Okay. And on the exams, you're not going to have to do like an 18 by 7 on the. That would be horrendous.
For the second matrix, which one are we using like as the pivot that we can work below?
This one?
Okay, so you can change the row that the pivot's in.
Oh, yes. So once we've cleared out zeros under the first one, then we're looking in the next row for the leftmost non-zero, okay? So this is the leftmost entry on the next row. Unfortunately, that is a 0, so I need to see the next. This becomes the next leftmost non-zero. And so then the goal is then eradicate anything underneath him to be 0. We happen to be able to do that really conveniently because they're just in their own rows by themselves, so they cancel nicely. But even if the cancellation wasn't as convenient, the strategy is still the same. I would perform necessary operations to eliminate that 9 and make it 0. And then I look at the next row. Well, that next row was all zeros. What's the leftmost 0? None of them. So no more pivots, we're done.
So like I get everything, but like what exactly is a pivot? How do you say?
Pivot?
Pivot.
The pivot's going to be the topmost and leftmost non-zero entry for your row. So for each row, it's going to be the leftmost non-zero term. We also call that a leading term. So,
okay.
Yeah.
So wait, so for row 1, that will be 3, right?
Yes. So this is the first one, and then we clear out zeros underneath that pivot. And then after we do that, we then return to our matrix and evaluate what the next pivot should be. So I would then go to the second row. And so I'd say, all right, that is not, that's a 0, so that can't be it. So then I move to the next leftmost. This becomes the next pivot. So then I say, all right, I need to get 0 below it. And so that's what we did here. We ended up getting 0 below it.
And then what about like the first matrix and the second row? Which one will be a pivot? Like in the second one.
Gotcha. Oh, this one or this one?
Yeah, no, the first one.
This one?
Yeah.
Well, I'm going to go to the topmost, leftmost, non-zero entry, and you're going to be your first pivot.
Oh, but can you do the same for the second row? Or?
Yeah. But because I know that these are going to be zeroed out. But in the process of zeroing these out, I don't know whether or not this is actually going to be a non-zero entry. So only worry about one pivot at a time. I think that's going to help. Take care of one pivot at a time, eliminate the zeros underneath one at a time, and after you do so, then come back to your matrix and reevaluate what that leftmost non-zero is going to be in the row. Does that algorithm make sense, John?
Would it still be correct if you switch the bottom 2 rows around and you did the same thing? You ended up with things in the exact same position as before.
So you want this to flip like that?
If you go to the third matrix, technically the same thing. If you're switching the 2 rows around.
Yeah.
Yeah.
Either way, you're still selecting the leftmost non-zero and eliminating underneath. These are good questions. Anything else I can clarify? Yes.
This is probably pretty obvious, but why when we change the original to subtract or multiply to the next, the original doesn't actually change?
Oh, I see what you're saying. So it's like, why am I allowed to double this and it doesn't affect the values of the other thing?
Yeah.
It's because of what we're replacing. So what would happen is if we did do this and replaced row 1, suddenly that's a problem because I'm now asking, am I using the doubled value of row 1 or am I using the normal value of row 1? So long as the row that you are replacing with doesn't get affected or you're not replacing and using that one, you will be fine. So for example, I have fixed row 1 to be the one row that I'm going to leave alone. I'm not going to replace it with any new values. And so knowing that it's not going to be replaced with any new values, I can essentially think of all of these constants in that first row as unaffected. They're constant. And so that's why I can then use it as a constant to adjust to replace the other rows that are not being held constant. Yes. Any other questions for this stuff? Okay. So we're almost done here. Now we need to clear zeros above and below this pivot. So I'm going to get rid of that 5. And we can do that by taking, we can take row 1, which is worth 5, and subtract 5 times 1. So subtract 5 times row 2, and then re-replace row 1. So then that's going to leave me with 3 minus 0, 5 minus 5, minus 4 minus 0, and then 0. And then 0, 1, 0, 0, 0, 0, 0, 0. And then if I want to now get this all the way to row reduced echelon form, this needs to be what value?
1.
Okay, so I can just scale everything down by?
3.
Yeah, let's scale it down by 3. So I have 1, 0 minus 4 thirds, 0. 0, 1, 0, 0, 0, 0, 0, 0. Is everybody happy with start to finish with the augmented matrix? Okay. So now what we want to do is get in the habit of thinking about this, the row reduced echelon form, in terms of its equation representation. So x1 minus 4 thirds times which variable? 3, yeah, is equal to 0. And then x2 is equal to what?
0.
And then, what happened to x3? Okay, so if I represent this in its parametric form, I would say that x1 is equal to what?
4 thirds x3.
Yeah, 4 thirds x3. I would say that x2 is equal to,
0.
and I'd say that x3 is what? 3. Ah. Now if you flip back, yes.
So earlier, when I forgot your name, when he asked about why you couldn't do two R1 plus R2 equals that situation over there. Over here, you were able to multiply R1 to get R1. Is that because there's no other row at play? Over where you do R1 by a third equals R1.
You are able to replace into the same route, yes.
But you could not do R1 times a third plus R2 equals R1.
Okay, I see the question.
Okay.
Here's what you're not allowed to do.
Okay.
I'm not allowed to say R1 plus something and then replace another row. And then say I change R2.
Okay.
What I would not be allowed to do is then go on and use the changed row in the
Oh, I
same
see.
step.
I see.
Because suddenly now you haven't let it reboot and then get you fresh numbers so that those will be correct.
Okay, but even under normal circumstances, you can still like multiply them.
Yeah.
Okay.
Yeah.
Thank you.
So long as you are not impacting a row and then using the impacted row in the same step. Because otherwise your arithmetic's gonna like have a total heart attack. Yeah.
In that, in the solution where the third row is all zeros, does that mean that all solutions are possible? Is that what that means?
Well, interpreted literally, 0 times x1 plus 0 times x2 plus 0 times x3 is in fact equal to 0.
Right.
All this is saying is that it's consistent, we don't have a contradiction, we don't have any problems with that, and so that's going to let us know we got a free variable.
Thank you.
Yep. So if you got a 0 row, something's going to be free. In this case, it's x3. Yep. And so now I want to show you how to represent a solution set in the vector form. The vector form is going to be way more useful. So x as a vector is going to have 3 components in this particular system. It's going to have x1, x2, and x3. And so when you solve these problems, write this step. Because if you write this step, it's really difficult to get these problems wrong, right? Because all you got to do is substitute all the work that you already know. What is x1?
4 thirds x3.
4 thirds x3. What is x2?
0.
And what is x3? It's x3, right? So whenever you have a free variable, he can stand in for himself. He's a big boy. Okay, and then what we want to do is we want to factor out the free variable as a constant multiple out front, suddenly this becomes what?
4/3, 0, and 1.
So the solution set, there are an infinite number of solutions to that system of equations, and all of them can be found by some scalar multiple of this vector. So this vector alone, scaled to any size, will solve that system. Yes, Denzel.
I'm confused because how I read that is x1 is equal to 4 over 3 x3.
Wait,
So,
which one are you at?
the one in the bottom.
This?
Yeah.
Okay.
So does that mean x3 is equal to x3, which means that which means that the constant is 1, or
Think of these entries as just constants. So there are no special properties here. So x1, the reason why I'm able to put 4/3 x3 here is because I'm just reading off of my parametric description of the solution. Where did I get the parametric description from? Well, it's basically restating this. Where did I get that from? Well, that is just literally denoting what it means to have this row reduced. Where did I get this? From doing a whole bunch of stuff from here. And where did I get that from? Well, the original problem gave me a system of equations. So you see the domino chain? All the way down to here.
So free basically means that x3 is x3. It means that it could be anything.
Anything.
0 times any constant is 0.
Yes.
Okay.
So I could choose 4 times the square root of pi. Does that break anything? No, because that just gets factored out as a constant times this. Okay? Now, if you watched the lecture, which you certainly all did, on span, then you'd recognize that this solution set is actually a span of this vector. Because by definition, if I take every single possible linear combination of that vector, so if I take whatever, it doesn't matter what it's scaled by, that's just what we meant by span, all possible linear combinations. So I could really think of this as the span of that one vector. 4/3, 0, 1. Which means that the solution set is in itself graphically just a line. Anything that falls on that line becomes a solution to here. And that's far more interesting than just having 0 as the trivial solution.
And that means that the line is. So I'm confused. So does that mean the line is from the origin to 4/3, 0, 1, denoting that the variables is x1, x2, x3?
That line is going to be generated by, if we imagine these as points, which you shouldn't think of it as a point because they're different from a point vector, but if you put a point at the head of each vector and scaled this to any constant, then all of those points would form a line. Yes.
Scott, sorry, I have like a slight side question. I just want to make sure whatever. So the reason why we don't have to zero out the negative 4/3 is because we don't have a pivot in that column, right?
Yes.
Okay.
Everybody, that's a very, very good question. What is in the next row? So we took care of the second row. Here's the third row. What's the leftmost non-zero entry? Does that work? Does that work? Does that work? Does that work? So what we say is that this row has no pivot. Okay? And so yes, that's why we're allowed to just have a random number floating over here, because, I mean, it's kind of just collateral damage from doing all the arithmetic, and then there's no pivots. If there would have been like a 7 here, that is a pivot suddenly, and then we would clear it. Yes?
So for the 8 to the 6, I can understand why we divided by 3, like R1 by 3, but from second matrix, the fourth matrix, why aren't we doing 3R2 minus R3 goes to R3?
Oh, if we're talking about in terms of just efficiency, you can get from here to here however you want. So long as you get here, every single one of these row-reduced forms is unique to every single system. So if you chose to take a different route, you don't have to do exactly how I do it here on the board. I just need to choose some way to get through the computation. But if you're able to get to this row-reduced echelon form through other steps or maybe faster methods, or you could do more mental arithmetic, that's totally fine. Yeah. So long as you get to this.
So you're just breaking it down so that you can understand.
I'm breaking it down because I myself am a really terrible mathematician, and I cannot do more than 2 computations in arithmetic at the same time. You think I'm kidding, is the best part. Okay. Does this example make sense? So now we've gone from doing parametric solutions to doing now expressing a solution as in itself a span of something. Linear combinations. All of the sections working together, which is really horrible if you're behind on watching lectures. Okay. Let's move on. Can someone grab me a time real fast?
51.
Oh, Lord. God have mercy. Okay.
2-hour video posted. 2-hour extra lecture posted by 8 p.m. today.
What if we make it 5 hours?
How many math classes are you doing right now?
One.
Like this one? Okay.
Yes.
Okay.
I'm not a math geek.
You said it's 150?
151.
Okay. So let's lock in, guys. Let's lock in. Let's describe the solution set of 10x1 minus 3x2 minus 2x3 is equal to 0. This, believe it or not, is a system of equations. How many equations? How many variables?
3.
Okay, so if I wrote this as an augmented matrix, I would have 10 minus 3 minus 2, 0. Would I not? Okay. What's the leftmost non-zero entry? Okay, so I could row reduce this by scaling everything down by 10. So 1 minus 3/10 minus 1/5, 0. Okay. I know this is probably a really weird looking matrix. It still is a matrix, okay? So I can write this as x1 minus 3/10 x2 minus 1/5 x3 is equal to 0. Now, let's do this parametrically. So parametrically, I have x1 is equal to
3/10 x2 plus 1/5 x3.
Very good. And then, what about x2?
Could you say that x2 and x3 are free?
Yes, x2 is free, and so is x3. I crossed out the free instead of the under the line. Okay, that says free.
Stop.
What if we start from x2, like we just write x2 equals to all the other stuff?
You can do that too. Yeah.
And
So
the other stuff becomes free?
yeah, Agnel is saying, what if I wanted to be biased toward x2 and make everything in terms of x2? Okay, so what's x2 gonna be? Well, you'd have to redo the, constant and stuff. But you could write x2 out in terms of x1 and x3, and I could say x1 is free, and I could have x3 is free. It doesn't matter. But you're guaranteed to always have the same. Notice, how many free variables do I have? 2. How many free variables? And so even if I did this, maybe I prioritize the x3 perspective and I write x3 out, you're still going to be stuck with 2 free variables either way. Okay? Now, that is all going to become irrelevant because when I write this as a vector solution set, it'll ultimately boil down to a span again. So, the vector x, how many entries should I put in for the vector?
3.
Yeah, x1, x2, and x3. Okay, what is x1? Let's use the top one for now.
3/10 x2 plus 1/5 x3.
1/5 x3. And then x2 is,
x2.
I'm going to write it over to the side. And technically, let's keep parallelism. So this is 0 x3. Okay, and then what about x3?
x3.
Yeah, 0 x2 plus x3. Does here to here make sense for everybody? Yes, okay. And why did I do that? Well, because I can split that up. I'm going to put all of the x2s together and split them from the x3s. So then I have 3/10 x2, x2, and 0 x2. Plus, okay, so you see this pattern, so follow the pattern. What's this one?
1/5 x3.
1/5 x3,
plus 0x3 plus
0,
x3. Yeah.
and then x3. Okay, so again, what did we do in the previous example? We factored out the free variable, okay? So if I factor out x2 in the first one, what's left?
3/10, 1, 0.
Okay, and then somebody other than Samika. After I factor out this free variable, what do I get?
1/5, 0, 1.
Beautiful. x2 and x3 can be whatever we want, yeah? And they're just a constant multiplied by a vector. Gee, that sounds like a linear combination of two vectors. Gee, sounds like I can take any possible one of these linear combinations of those two vectors. Gee, that sounds like the definition of a span, okay? This is the span of which two vectors? Which two vectors are being allowed to take linear combinations of that are arbitrary? 3 10s, 1 0, and I did not plan that in my head very well. Let's back this up. The span of which two vectors? Come on.
3
And what's the other vector?
1/5, 0, 1.
This is our solution. Which if you watch the lecture, then this is a plane geometrically. So any point on that plane satisfies this really funny looking system of equations. Okay?
Yeah. How do you know there's only 2 free variables rather than 3 variables in that solution?
Good question.
Like there's only 2 variables in the linear system, right?
Well, so the original system of equations, we are upfront told that there's at least x1 through x3.
Yeah, and 2 of them are free variables, right?
Yes.
How do you know there's only 2 variables rather than 3 variables?
Good question. I take the number of variables that there are, and I subtract the number of rows I have in my row reduced. So how many variables do I have in this equation?
Oh, there's
3.
oh, 3.
How many rows do I have? I have only 1 row. So I take 3, I subtract 1, that gives me 2. So that means I'm missing 2 whole rows that would have given x2 and x3 basic solution. And so that's how I know that I'm going to anticipate there being 2 free variables. It's a good question. Yeah, because if I had say I row reduced, so it's in row reduced echelon form, and I had 4 rows and 8 columns, even after everything's row reduced, well, I think to myself, oh shoot, 8 columns, I have 8 variables, but only 4 of these are receiving, there's only 4 rows. So 8 minus 4 is 4 left over. 4 variables aren't getting a basic treatment, so they're just going to be roaming free, while the other 4 are basic, or in terms of the other 4. Okay.
I got a question.
Yes.
So how do you know for a fact that you're doing x2 and x3 in the span without notation of x1?
Are you asking how I know that this is a span, or are you asking how I know I can use x2 and x3 specifically?
I'm asking where you literally put the word span. How do you know that you're saying not x1, x2? You know for a fact you're saying x2, x3.
Good question. I am being a little bit generous with notation right now. If I wanted to be fully rigorous, what I would do is I would put set bracket notation like this, and then I would say such that x2 and x3 can range and be whatever real number we want. So that makes this then, by definition, what it means to be the span of those 2 vectors.
So for the answer, to put the actual correct answer, we need to put on the other side of the.
Yes. If they ask specifically for the span notation, follow the definition of span. So you would want to make it a set, and then have your constant times the vector plus constant times the vector, and then such that your constants can range over the real numbers. They might not use x2 and x3. The textbook likes to switch these out for R and S or T or U or something like that. The actual number at that point doesn't matter because we know that they ultimately just range over R. Does that make sense?
Yeah.
Okay.
And is there like a way to like imagine it? This might be a dumb question, but like how I see like the first part is you're basically making like a unit vector-ish when you're going down of like of it intersecting.
What we don't want to do is think of this as a unit vector. I will tell you that much. Yeah.
Is that part of the answer, or is that you saying like what, like the right part, like after the matrix 1/5, 0, 1, the x2, x3.
In R?
Yeah. What does that mean?
What this means is I'm saying that if I'm going to have x2 and x3 here, I might as well explain what they're allowed to be. Well, they're allowed to be anything. So I'm just simply saying that both x2 and x3 can be real numbers. So in math, this is saying x2, comma, x3 in R, the set of real numbers, yeah. So there's a lot of different ways you can express that, either with words in English or just conceptual understanding, yeah. Okay. These are good questions. Anything else? Was that a question from Jacques in the back or no?
Oh, no.
Okay. Okay. Is this starting to make a little bit of sense? Tying everything. The first chapter of linear is kind of frustrating because you'll go through the first 4 sections or so, and you're just being expected to have hindsight on what you're looking for. So the first round is a little rough, but as you review, this is going to be, it'll make more sense in hindsight each passing time. Which is just life, actually, in general, so. Okay, can I get a time, please?
Time is 02:01.
We're at 02. Oof. Okay. Okay, so what I'm going to do, I'm going to leave this up to you, actually, okay? Do you want me to kind of speed through an example, but I won't really be able to explain much? Or do you want me to later actually record a full explanation of everything on the last half of the section?
Wait, can you hold that up for a second?
No, I could just take a picture of it. And
I can take a picture of it.
I have...
Oh, dear God, no.
Okay, do you guys want to speed through it, or do you want an actual just recording of the full explanation?
Probably.
Recording? Okay. A few people want me to speed through it, so I'm going to speed through it because we're still hearing that, alright?
We're gonna have both.
Describe. If we're going to speed through it, I'm going to need you guys lock in though, okay?
Okay.
All solutions of AX is equal to B. We've changed it up. We've introduced a not zero necessarily vector. So where A is 3 minus 3. Okay, honestly, let's just reuse the matrix we just did. So 5 minus 2, 1, minus 4, 4, minus 8. But this time, we'll use a non-zero vector. So 7 minus 1 minus 4, like that. So then the augmented matrix is 3 minus 3, 6, 5 minus 2, 1, minus 4, 4 minus 8, dot, 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 right? Because then we have B, which is 7 minus 1 minus 4, which row reduces to 1, 0, 0, 0, 1, 0, minus 4/3. So those constants should look familiar. And then the constants over here will come out to minus 1, 2, 0. If I want to express this now parametrically, and in case you're wondering, no, I did not just do that in my head. I have cheat sheet, okay? But you could go through all the computation if you wanted to, and you get those numbers. So parametrically, the solution, I've got x1 minus 4/3 x3 is equal to minus 1 now. I've got x2 is equal to 2 now, and then I still have a free variable, so I could say I've got x1 is equal to 1, or sorry, minus 1 plus 4/3 x3. I've got x2 is equal to 2, and x3 is free. This is parametric form of the solution set. Now I'm going to write it as a vector. Same o, x1, x2, x3. x1 is minus 1 plus 4/3 x3. x2 is equal to 2 plus 0 x3. There's no x3s. And again, I'm creating this parallel structure so that when I decompose it, it makes more sense. And then x3 is just x3. So no constant, and then I have x3. Decompose constants and the others. Minus 1 to 0. Those are all the constants together. Now all the x3s together. 4/3 x3. 0 and 1. Factor out I miswrote that actually. That's x3. Now we want to factor out the x3, and I get minus 1 to 0 plus x3 factored out, 4/3, 0, 1. Now, this should look really familiar, should it not? Didn't we just spend like a lot of time reaching a solution that was 4/3, 0, 1? And that just happened to so be the solution that we could scale it, and it was the solution to the homogeneous version using this matrix. So if I would have chosen B to be the 0 vector, this would have been my solution anyway. Yeah? Does anyone see that? It's kind of suspicious, is that not? And it's actually the same thing. I'm scaling that same solution, which would have been the solution if I would have cleared B to 0. So that really makes the only difference between the solution sets a singular vector. So if the difference is only between a singular vector, what's happened is I've taken the solution set to the easier version of the problem, which is the homogeneous, and I've translated it up by a certain distance. And so these solution sets are together, they're parallel. And the only difference between the homogeneous and non-homogeneous solution sets is some sort of shift by some amount by a vector. Okay? And so what the textbook is going to do, and what I'll talk about more later, because there's a little bit more I could say, is in general, when we're now moving from the homogeneous version of the problem to a non-homogeneous version of the problem, you should anticipate it having a very, very close relationship to the homogeneous version of the problem. And the reason we like those kinds of relationships between easy problems and hard problems is because the difference between the outcome of an easy problem and a hard problem is just one tiny little detail. That suddenly makes the easier version of the problem all that much more powerful, because that gives you access to an otherwise much more difficult solution through some conceptual understanding. So I will record something really brief later that just covers the algorithm for solving and a few more details on theorems. But other than that, that is pretty much the section. So we hit 1.7 on Friday.
I am so long.